number. Anyway, so this shows that this Bose-Philipperson algorithm may not work for the, general case when capacities of the network are not rational. But what's the problem here? Why it didn't work? The problem is we have taken long passes, long augmenting passes. So when a network is given, there may be more than one augmenting path. Then you have to make the decision whether to go with this augmenting path or the other augmenting path. But in the above example, we made the wrong choice. So we can actually improve this algorithm by giving instruction to choose the right augmenting path. So which is Edmonds Karp algorithm. So let say D be a, let's say just G, be a network with say n vertices and m edges. For each I, we take the flow Fi. This is obtained from, say, Fi plus 1 is obtained from Fi by augmenting along a shortest augmenting path. Then the algorithm must terminate. And it takes less than n times m over 2 repetition. So what this theorem suggests is that whenever we have a situation that we have this flow and then we want to choose an augmenting path, we always choose the shortest augmenting path. There could be more than one shortest augmenting path, but you can just choose any one of them. Then this says that we can actually, find the maximum flow within the fixed number of steps. So we want to prove this. Before proving this, let's prove a useful lemma. So let D be a, say, multi-digraph. So digraph possibly could have a multi-edges. And let's say S and T are the vertices in this digraph, such that the out degree and in degree are same for all V except S and T. Excuse me. And moreover, for the vertex S, out degree is bigger than in degree by K. Then what we claim is that this digraph, in this digraph, we can find K edge disjoint passes from S to T. Directed path from S to T. So why is this lemma true? is that, okay, just consider the case when k is 1. We want to find just one path. We have this S, and here, we just move to another vertex. And then, once we keep moving, and then once we hit T, then we are done. If it never hits T, then what happens is that we have to end at certain vertex. Because, there are finitely many vertex, so we must end at some point. But because of the condition that the in degree and out degree are same, once you get in, there should be another edge which we never used to get out. So assuming we don't use the same edge twice, we should be able to keep go until we cannot anymore. But as soon as we are at the vertex which is not T, we can keep go. And once we know this for k equal 1, then we can take one edge from, one path from S to T, and we delete the older edges. And then this condition satisfied with k minus 1. There you repeat again. So inductively we can prove this. So let's just write it. We use induction on k. I think we don't need to really write it down, but because I already explained you the idea already. More fancy way of writing it is that we let X be the set of vertices which you can, which with the property that there exists a directed path from S to X. If T is in X, then we just simply take a path from S to T, and then we delete all the edges, and then we use induction. We already find one path, so we can keep repeat. Otherwise, if T is outside of this, then we consider the subgraph induced by this set X. The property is that for all X in this X, all of this is not our neighbor is again in X by the property. Because, if there is Y and then there is a directed edge from X to Y, then the path from S to X plus this one edge give us a path from S to Y. So Y also have to be in X. So this shows that in this graph, in this induced subgraph, say D prime, degree of X in out degree is at least as large as its in degree. Because this is same as degree of X in the entire graph, but this is actually smaller than this. Because this is at most neighbor, the in degree of the original graph. So we have this inequality. So this D prime is a graph satisfying this inequality. At every vertex, its out neighbor, out degree is bigger than in degree. And in S, the one vertex S is strict inequality. Strict inequality. However, we already know that the sum of out degree in a directed graph must be same as sum of in degree, because both of them counts every edge exactly once. So which is a contradiction. So this cannot happen. So that means T must be also in this X. So we can find the ST path and we delete all the edges and then we repeat it. So this will prove this. So a formal proof is in the lecture notes, so you can read it. So with this lemma on our hand, now we want to prove this theorem. So this is the theorem that we want to show. So assume we have, okay, before doing that, let's define one more terminology. So let P be on, say, F augmenting path. So flow F is given, and P is F augmenting path. And the flow F is increased along P by amount epsilon P. So that's the amount that we increase. Then there are at least one HE which kind of becomes, say, saturated. Meaning Fe plus epsilon E is either the capacity of E if E is directed towards T, or f of E minus epsilon P is 0 if E is directed towards S in P. So there must be such an edge. We say such an edge E is a bottleneck edge for P. So meaning that when we have this path, and then its capacity is, say, 5, 2, 3, 3, 2, 4, and then flow is like 2 going here, of 1 going here, 2, 1, 2. And then let's say we take this augmenting path, and then we say increase by 1, plus 1, plus 1, plus 1, plus 1, sorry, minus 1, plus 1, minus 1. Let's say this was 1. Then after doing this, this becomes 3, this becomes 2, this becomes 0, this becomes 2, this becomes 1. So we added and subtracted this 1 because that's the best possible. We couldn't do more. We couldn't do more because of these 3 edges. If we added more, then this would be bigger than its capacity, and this would be bigger than this capacity. And if we subtracted more, this would be non-negative. So those 3 are the reasons why we couldn't augment more. And we call them bottleneck edges. So now we want to prove the theorem. And let P1, P2, and say P sub P be a sequence of shortest augmenting ST passes. where pi is a fi minus 1 augmenting path. And yeah, initial flow f0 is given. That's what we assume. What we want to show is that this must end. For that, how we want to show? We want to show that the length of these paths keep increase. So ideally, what we want to show is that if this keep increase, then all these numbers, the length of the paths are integer, so this must end. But showing this strict inequality is difficult. So what we want to do is that many cases this inequality could be equality, but some cases once in a while this must be strict inequality so that we can actually get a contradiction. So that's what we want to do. So we want to essentially prove two things. First is that this keep increase. And two is that for certain cases, these are strict inequality. The certain case is, that we want to show that if E is a bottleneck edge for both Pi and Pj with j bigger than I, then we want to show that this is strict. So that's roughly what we want to do. For that, let's prove this claim. This claim is useful to show those two. So assume that we have this Pi and Pi plus L. They uses say k edges in opposite direction. So there are E1 to Ek, and then each edge is inside of this path. So, but at one it's traversed in one way, and the other is traversed in the other way. But for any, say, j and j prime, which is nested between these two numbers, with j and j prime is not I and I plus L, the path Pj and Pj prime do not use any edge in opposite directions. So this is what we assume. Then we want to claim that the number of edges in I plus L is at least the number of edges in I plus 2k. In application, we will only use the case when k is either 0 or 1. So we have this two passes Pi and P. So this is Pi let's make it a bit longer. And let's say we have this Pi plus L. Then what we want to do is so on here this is in opposite direction. So remember that this does not necessarily mean, okay, let's say this does not necessarily mean that this is UB. This does not necessarily mean that the UB is oriented in this direction in the original network. So this does not necessarily mean that. So this means that in Pi, it's from U to B. So this, this is just in this path. Okay, and now from here, what we want to do is that here, this H is traversed by the opposite direction by this 2, then we want to just simply delete it. And then everything else we keep it, and then we keep this as a multi-edge. And let the resulting digraph be H. So H is not necessarily a subgraph of D, because these edges may be oriented in other ways in the original digraph D. So form a new digraph H from the H of Pi union with H of Pi plus L by orienting all H's towards T and taking twice any common edges. And removing K common edges which are passed by those two vertices in the opposite direction. Then what happens in this graph? In this graph, for every vertex, there is one incoming edge, one outgoing edge, one incoming edge, one outgoing edge, and two incoming edge, two outgoing edge. So every vertex, its in degree and out degree are same. On S, its out degree is bigger than in degree by 2. on T, its in degree is bigger than out degree by 2. So we may use this lemma 1.11 because all the internal vertices have the same out degree and in degree same, and then source has larger out degree than in degree by 2. So this says that by lemma 1.11 we can find two edge disjoint passes Q1 and Q2 from S to T in D, where the union of those edges actually lies in the union of these two paths. Now what we want to claim is that some of the edges are lost. When taking union, we deleted k edges, k common edges. And then we find the two edge disjoint one. So one of them must be shorter or same length or shorter than pi. But pi was the shortest f augmenting path. So from there we want to get a contradiction by showing that the q1 or q2 are actually augmenting paths. So we want to claim that for each j, so q1 or q2, the path is f sub I minus 1 augmenting path. So again in D, this might be oriented this, but P or Q could be this path. I mean, augmenting path is directed in this way. So why is it? So to show that this is fi minus 1 augmenting path, we have to show two things. For all fold-oriented paths, oriented edges, the flow value is smaller than capacity. And for all reversely oriented one, the flow value is positive. So those two are the things that we want to check. First, that's what we want to check. First, suppose that an HE is traversed along QJ from tail to head. So meaning that in D it's oriented this way, and then in Q it's also oriented in the same way. So in this case, we want to show that the flow value is strictly smaller than the capacity. How do we show it? We show this by using the fact that the pi and pi plus 1 are augmenting. So again, there are two cases. If E is in pi, then we know that Qj and this pi traverse E in the same direction. So E is in Pi and E is in Qi, and then they use this in the same direction because all the remaining edges here are traversing in the same way in Pi or Pi and Pi plus L. So what do we know? E is part of Pi, and then Pi is Fi sub I minus 1 augmenting. So we know that this inequality holds. Once we augment Pi to get Fi, the value of E increases. And then at the time, what we get is a feasible flow. So this number is actually at most the capacity of E. So we have that in Fi minus 1, its value is strictly smaller than capacity. And the other case is that if E is in Pi plus L, but not Pi, then what do we know? In the theorem, we assume that in the claim, we assume that this. For any j prime, which is between I and I plus L, they don't share any edges. By the hypothesis of the claim, that hypothesis, we know that E does not appear in any of Pi plus 1, Pi plus 2, up until to Pi plus L minus 1. If this appears in one of them, in say Pj, then say Pj prime, then here we could have taken j to be I and then j prime to be that j prime. Or the other way around. We take I plus L as 1 and the other way. So if this one was Pj, then we could have taken j and then I plus L plus 1. J prime equals to I plus L. So which would be contradiction to this assumption. So this E does not appear in any of this. Why is it important? It's important that this means that E is not even in Pi, so its value is not changed once we augment the flow by using Pi. And then its value also stays same once we augment by Pi plus 1. All the way to here, and then its value is same with Pf sub I plus L minus 1. But at this time, we augment it by Pi plus L to get the F sub I plus L. So this is P sub I plus L is an augmenting path, means that this value is strictly smaller than CE. So this concludes that F sub I minus 1E is smaller than CE. So in both cases, we get this. And the other case is if E is traversed along Qj from, say, head to tail. In the same argument, we can actually check what we want. That this is actually has a positive flow value. Fi plus 1 has positive flow value at E. So we conclude that this Qj is actually Fi minus 1 augmenting path. And Q1, Q2 are also considered as a candidate to be Pi, but the Pi is by definition shortest augmenting path. So this was considered for the, say, let's try it this way. Together with Pi for the choice of shortest f sub I minus 1 augmenting path. So we know that they are not shorter than Pi. From that, what we have is that twice times Pi is not bigger than the number of edges in Q1 and Q2. And then the Q1, Q2 are the composition of this directed graph H. And how we obtain is we take the edges of Pi and we take the edges of Pi plus L, and we deleted all the edges which are opposite direction in those paths. From here, what we get is that Pi plus L is as large as Pi plus 2k. So this proves the claim. So from this claim, we can actually show our desired claim. So first, we can show that Pj is bigger than Pi, bigger than or equal to Pi, if j is bigger than I. And then, let's say if Pi and Pj uses an edge in opposite direction, then Pj is strictly longer than Pi, let's say at least by 2. So A is easy because by the previous claim, we have Pi plus 1 is longer than equal to Pi because I and I plus 1 satisfy this condition. So this second condition is trivially satisfied for I and I plus 1. And then they shares at least 0 number of edges in opposite direction. So you just apply that, then you get this inequality. And then you do that until you get Pj. And then to show B, and again so they uses one edges in opposite direction. Then take I prime and j prime so that the I and I prime and j prime j such that pi prime and pj prime uses same edge in opposite direction. And among the choice, j prime minus I prime is minimal. Note that the I and j satisfy this condition. So there should be a pair with the smallest this. And we apply previous claim. Then what we get is p j prime plus 2 and p I prime 2. Pj prime has a length larger than pi prime by 2, and then by A we know that these two inequality holds. So from this we will know that the Pj has length at least 2 more than Pi. So now we are all equipped to prove the theorem. So as P1, P2, PP is a sequence of shortest augmenting paths. Each Pi contains at least one edge, say EI, where it is a bottleneck edge for Pi. Meaning that the flow value in this EI, this becomes 0 or its capacity after augmentation using this Pi. And for an HE, let's say Pi1, Pi2, and Piq be the subsequence of all Pi's in each of which he is bottleneck. And if Pij and Pij plus 1 use E in opposite direction, then obviously the previous claim says that the length increased by at least 2. And if this and this use E in the same direction, then what would it mean? When we augment it by this, E end up having the value either 0 or the full incapacity. And then there are other P ij plus 1, ij, other path augmentation we did, and then right before we are doing this augmentation, it's again bottleneck edge with the same direction. That means its value has changed before. Its value has changed before by other path P prime, where the E is not a bottleneck edge for this, but this has changed. But when this Fij of E is already, say, full, and then we make the further changes on this value when we augment by this P prime, then this has to go down. And in other case, if this was 0, then in other changes, this has to go up. So in any cases, there must be J prime between Ij and Ij plus 1 such that Pj prime use E in an opposite direction. Opposite direction from where these two paths use, direction where these two paths use E. So again, by the previous claim, we have this at least E of Pj prime plus 2 is at least P of Ij's length plus 4. So what does this mean? So we assume that there are Q many paths using E as a bottleneck edge, and we just show that every time the length increases by 2, and then the length cannot be bigger than n. So we conclude that this Q is at most n over 2. So if there are m edges in D, and each edge can be a bottleneck edge for at most n over 2 passes in the original sequence P1 to P. Hence, P is at most mn over 2. So this proves that this algorithm must end with at most mn over 2 step. This proves the theorem. So note that here the number of steps is independent of the capacities. So even if some capacities are very large, it's still okay. But the Fold-Pirocason algorithm, the number of steps is actually dependent on the capacity. And also here, as an algorithm, one step is missing. We should be able to find the shortest augmenting path, which is actually possible by considering the breadth first search tree. So when we have D and you have this network, And then you have this flow. Yeah, it's difficult to write the numbers so that the rule satisfy. But when we have this, let's say some number, what we do is, so here, this flow value is 1 out of capacity 2. So it can either go up or down. In that case, we add the 2 edges in both directions. And then here, we can only go down. Then we take only opposite edge and we add. And then here, again, we both direction. And here, this is 0, so it can go up only. So we take the edge with the original direction, but not the other direction. Then you can create another directed graph here. In this directed graph, if we find the path from S to T, then that path is automatically F augmenting path. So finding F augmenting path in here changes to the problem that finding a path from S to T in this directed graph. And finding a shortest path from S to T in a directed graph can be done by breadth first search tree. Breadth first tree search, yeah. Breadth first search, yeah. That's I think proper name. So what you do is you take S and you take all its neighbor. And then for each one of them, you take again all of its neighbor, which is previously not taken. Even if this is our neighbor, you don't take it because this is already there. One by one, one by one. So you find all the vertices which is reachable by distance 1 from S, and all the vertices which is reachable from S by distance 2 from S. And you keep do that until you hit T. By doing this, you check all the vertices with which can be reached by 1 step, and all the vertices reached by 2 steps, and so on. And first time you hit T, you automatically find the shortest path. Because if there were a shorter path, you would have hit this T before the moment. So if you hit this T at the first time, then that gives you right away the shortest path in this directed graph, and then that yields this F augmenting path. To finding this can be done in M steps. For each edge, you replace it with 2 edges or 1 edge in here. So constructing this takes M step. And then once you constructing this, you take S, and then you take all its out neighbor 1 by 1, and then out neighbor 1 by 1, 1 by 1. So you check all the edges at most once. So in M step, you can find the shortest path. So this algorithm runs in, say, n M step or n times M step times. Because for M, you can find the F augmenting path. And then how many F augmenting paths you have to find? This many times. Let's say this is not M, this is 2M. So big O of M step. So this provides an algorithm to find the maximum flow. So today we show that if the capacities of a network are all integers, then there exists a maximum flow with integral value. So which is useful as most of our applications are centered on the graph theory problem or combinatorics problem. So this flow integrality theorem is useful, that we know that there exists a maximum flow which takes integer value as long as all the capacities are integer. But if all the capacities are not integer, then we need, then the max flow might not be integral. And then proof of this actually yields a fourth Fulkerson algorithm. You take the augmenting path and augment, and you keep do that. But if all the capacities are rational, then this algorithm is good, but otherwise it may not terminate. In that case, we can actually do better by taking shortest augmenting path every time. You take the shortest augmenting path and you augment by that path, and then for new flow, you find the shortest augmenting path and you augment, and you keep do that. And then we prove that that algorithm actually works. So next time we will learn about the applications of this max flow Minkowski theorem in graph theory. We can actually use it to prove several well-known theorems like Mengel's theorem or the Koenig theorem or Hall's theorem. So those are the ones that we will learn next time.